In today's lecture, I want to talk about an important property of the Z-transform, which is the linearity of the Z-transform. So by now you probably know what it means for the transform to be linear, or in general a function to be linear, but I want to explain this in the context of Z-transform. And then we were going to talk about how to apply linearity to find the Z-transform of a sum of signals. And of course, what we learned from the previous lecture is that we need to always characterize the region of convergence of a Z-transform. So we will talk about characterizing the region of convergence of a sum of signals. And then we will also talk about the Z-transform of a special function such as the cosine and sine functions. So like I mentioned, the Z-transform is a linear function. So in general, a linear function for a general function, we say that it is linear if it satisfies the following property. So we say that f of x is linear if f of ax plus by is equal to a times f of x plus b times f of y. So this is general definition of a linear function, and the Z-transform does satisfy this property, meaning that the Z-transform of the sum of two signals, or the sum of two signals, is the sum of their Z-transform. Or you can also say in a more general way that the Z-transform of a weighted sum of two signals is the sum of their Z-transforms. So here it's written in this way. So the Z-transform of a signal alpha times xn plus beta times yn. So here alpha and beta are scalars, are complex numbers. So the Z-transform of this signal is alpha times the Z-transform of x of n plus beta times the Z-transform of y of n. So the linearity property follows immediately from the definition as it's done here. So here I prove why the Z-transform is a linear function, because it's basically a summation, and then you can take out the scalars alpha and beta outside of the sum, each sum, and you can split the sum here, and you get that the Z-transform of alpha xn plus beta yn is alpha times the transform of x of n plus beta times the Z-transform of y of n. So the reason why Z-transform is linear is immediate. What we still need to talk about is what would be the ROC of this Z-transform as a function of the ROC of x of n and the ROC of y of n. So the question now is, how can we find the ROC of a sum of signals, or a weighted sum of signals? As we have here, we have the signal which is alpha xn plus beta yn, and the question is, when does its Z-transform converges? And if you think of it for a second, you can find that for this weighted sum, the Z-transform of this weighted sum to converge, we need that both x of z to converge and y of z to converge. And for this reason, the ROC of the weighted sum is actually the intersection of both ROCs. So the ROC of this signal is the ROC of x of z intersecting with the ROC of y of z. So it's the overlap. And the reason is that because we need both signals to converge. So let's put what we learned so far into action, and let's work out an example. And the example that I have here is to find the Z-transform of the following signal, xn. And xn is equal to 1 over 2 to the n u of n plus 1 over 3 to the n u of n minus 2. Now you can see immediately here that this signal is actually two parts. The first part is this part here. This is signal 1, if you want to call it x1 of n. And this is part 2, which is x2 of n. So I know that either I can find x of z, the Z-transform, by just considering this signal as a whole, or maybe it may be a little easier by using the linearity of the Z-transform and leveraging the fact that this signal is the sum of two signals and working out the Z transform of each signal separately. And this is the method I want to do here. So first I want to find x1 of Z, and then find x2 of Z, and then I know that x of Z is the sum of x1 of Z plus x2 of Z. And this follows immediately from the linearity of the Z transform. So let's start by trying to find the Z transform of x of n. So like I said, I think of this signal as the sum of two signals, and I want to start by finding the Z transform of the signal x1 of n, which is actually this signal here. So this is x1 of n. Now what is the Z transform of this signal? So one way is to do it is to apply the formula, the definition. So, and you should do this every time you encounter a signal that you haven't seen so far. But this signal actually is going to be an example of a signal that we're going to see a lot from now on. So you can actually just apply the formula. And the formula, we remember it from last time, it was at the end of last lecture. We have that if a signal x of n is equal to a of n u of n, then the Z transform of it, so this is a right-sided, it's an exponential signal and it's right-sided and it starts at 0, so it's basically a causal signal. Then the Z transform of it is Z divided by Z minus A, and the Z and the ROC is the exterior of the circle at the amplitude Z equal to A. Again, this is the ROC because the signal is right-sided. And this is actually what I do here. So the Z transform of the signal is Z divided by Z minus 1/2, and the ROC is the exterior of the circle centered at the origin and with radius 1/2. Now let us try to find the Z transform of the second part of the signal, which we denoted by x2 of n. And that's what I want to do next. So what I want to do here is find the Z transform of the signal 1 over 3 to the power n un minus 2. This is again a signal that you've almost seen before. Then maybe the only little annoying thing is that here the step function is un minus 2, which means that the signal starts at n equal to 2. And what that means that you plug in the formula here, so the formula is going to start at n equal to 2, and the Z transform is going to be the sum from n equal to 2 to infinity, 1 over 3 to the n Z minus n, so just the formula. And then if you group it together, 1 over 3 and Z minus 1, to put it under the form that we know, which is the geometric series forms, then you're going to get that this is equal to the sum from n equal to 2 to infinity, 1 over 3 Z minus 1, all of it to the power n. And now I can apply the formula that I know. Just keep in mind that here the summation starts at n equal to 2, so you have to be careful. So the formula says it's the first term in the summation divided by 1 minus the ratio. So, and here the first term is going to be 1 over 3 times Z minus 1 square, because the first term starts at n equal to 2, so it's going to be 1 over 3 square Z to the power minus 2 divided by 1 minus 1 over 3 Z to the power minus 1. And now if you multiply by Z square the numerator and the denominator, you're going to get 1 over 9 Z square minus 1 over 3 Z, or 1 over 9 Z times Z minus 1/3. So you know here that you have actually two poles, a pole at 0 and a pole at 1/3. And again, the signal is actually a right-sided signal, so the ROC is the outside of the circle at 1/3. Now that we found the Z transform of both components of the signal we have, what we call x1 of n and x2 of n, we can find the z transform of the signal x, which is actually this summation of both z transforms. So it's gonna be, this is the first part corresponding to the first signal, and this is the second z transform corresponding to the second signal. And like we said, the ROC of the first part is the exterior of the signal with radius 1/2, which is here. So let me maybe write it down in a bigger font. So this is 1/2 here, and it's the outside of this circle. And the second part, which is this one here, the ROC was the exterior of the circle at 1/3 because it had pole 1/3. So this is why you have 1/3 here. So actually the ROC is outside this circle, everything outside, and you can see the overlap is actually at both, the overlap of these both ROC is the exterior of the outermost circle. So it's gonna be the exterior of the circle at z equal to 1/2. So this is the ROC of the sum. So to summarize, the ROC of the sum is the intersection of both ROCs. And here the first ROC of the first signal was z bigger than 1/2. So it was the exterior of the circle here. And the second ROC, maybe I'll use a different color, was the exterior of the circle 1/3. So it was here. And the ROC of the sum is actually the overlap. So it's gonna be, actually you can see here that the overlap is the ROC of the first signal. So it's correspond to the norm of z bigger than 1/2. So it's gonna be everything here. So everything yellow basically. So that's what I mean by the intersection or the overlap. I want to conclude this lecture by working one more example that is a little bit more, I wouldn't say difficult, but a little bit more interesting than we had before, which is the following signal. It's x of n is 1/3 to the power n sine pi over 4n u of n. Now you may think it's interesting because it has a new function, which is the sine, but then the question is, how is this related to the summation? And this is what I want to clarify next. So the trick in finding the z transform of these trigonometric functions is to use Euler's formula, which says that e to the power jx is equal to cosine x plus j sine x. So this is a super important formula to keep in mind. And here j is the complex number, which is the root or the square of -1. So j satisfies j square is equal to -1. So in engineering we call it j. Sometimes maybe you've seen it in math being called I. It's the same thing. So basically j, I mean, and another notation of it is this, is j is the square root of -1. So given Euler's formula, we can write cosine and sine as a function of, as exponential functions. So cosine x is actually the real part of ejx, which is equal to ejx plus e to the power minus jx divided by 2. So this is the cosine in green here. And the sine is going to be equal to the imaginary part of e to the power jx, which is equal to e to the power jx minus e to the power minus jx divided by 2j. So these are super important properties to keep in mind. And hopefully now the link to why I'm bringing up these in this lecture is demystified, because you can see actually that the sine and cosine function are actually summations. And then I can use linearity of the z transform to find the z transform of a sine function. Therefore, I can use Euler's formula to rewrite the signal that I was given, which was 1/3 to the power n sine pi over 4n u of n. again, this is a right-sided signal. It's actually a causal signal. To write it as a sum of signals. And actually to write it into sum of signals that I already know how to deal with. So I'm going to write it as a sum of exponentials using Euler's formula. So this is going to be equal to 1 over 2j 1 over 3 ej pi over 4 to the n un minus 1 over 2j 1 over third e minus j pi over 4n u of n. And again, to do this, if you're a little bit confused, I can do it a little bit more details here. So what I did is that I replaced sine by the formula of it that follows from Euler's formula. So this is 1 over 3 to the power n times ej pi over 4n minus e minus j pi by 4n, and then the remainder on u of n here, I forgot it, and then the remainder follows easily. So now let's get into finding exactly what the z-transform of x of n is. Again, I could do it the same way I did the previous example by splitting it into two signals, but here I'm just going to do it in one shot. So by just applying the z-transform, the definition of the z-transform. Again, so don't be scared by this. This looks a little bit complicated, but actually the key to solve this problem is to remember, if you see something like this in the homework or in the exam, is to remember Euler's formula. So here I'm applying the definition of the z-transform. So it's the summation of the value of the signal at n times z minus n. And by linearity, actually, I know that I can split these into two parts. And then also the summation is starting at 0 because I have u of n. I have the step function here, which is u of n. And now once I put it that way, you can see that I can apply the geometric sum formula. And both of these summations start at 0, so it's going to be easy. So it's going to be 1 over 2j here, 1 divided 1 minus this term here. Maybe if I highlight it, it makes it easier to see. So it's the term here is 1 divided by 1 minus this term here. And here it's the same thing, minus 1 divided by 2j, 1 divided by 1 minus this term, the term that is being highlighted in yellow. So again, so I'm just applying the geometric series formula and the Euler's formula. And then if you do a little bit of calculation, you get the nice formula of the z-transform of this sine-based signal. And of course, this is not the end because we need to specify the ROC. And the ROC of the green summation here is actually the norm of 1/3 ej pi by 4 z minus 1. So this is a right-sided signal, so it must be greater than 1. And for the yellow one, it's similar. So it's also, this part here is also a right-sided signal. So we need to have the amplitude of e minus j pi by 4 z minus 1 greater than 1. So, and this is what this slide is summarizing. So the first part has ROC given by this equation, which is actually give you that you know that the norm of EJ anything is 1. So this will give you that 1/3 norm of z minus 1 is less than 1, and this will give you that the norm of z is greater than 1/3. Same for the second part, and the ROC is the intersection, but both ROCs are the same, so we get the ROC of this summation, which is the original signal that we started with, to be z greater than 1/3. So I will end this lecture by a few problems for you to solve at home, and feel free to post the solution on Piazza. Like I said, in all this course and in all these lectures, just watching the videos is not enough. You really have to do it by hand and check the results. And also the textbook has plenty of examples and further exercises to practice. So it's very important to practice problems. So this, at least in this course, we're not focusing a lot on the theory, we're focusing on exercises and practicing, and I really recommend that you try to work more examples that you can find in the book or online, and in particular, I mean, you could I'm suggesting here 3 signals to find the Z transform of. The first one is an cosine omega 0 n un, and the second one is b to the power n cosine omega 0 n, and the second one is an cosine omega 0 n plus bn cosine omega 0 n. And please post the solution on Piazza.